I'm Elizabeth, and my presentation is on Jackson Pollock and fractal analysis. So to start with, who is Jackson Pollock and what has he made? Pollock was an American artist, and his most prominent years were from 1947 to 1951, with his most famous body of work being his drip paintings. So you can see an example of one of his most famous drip paintings entitled Number 1, often referred to as Lavender Mist, from 1950 on the top right, and a piece that acts more as a transitional work from his abstract to his drip paintings is called Mural from 1947, and that is on the bottom right. Then on the left, you can see Pollock in the middle of his drip painting process. There were a lot of people from different fields who were fascinated by Pollock and his work, such as art historians, physicists, and mathematicians. For art historians, it was how he changed how artists view the canvas. It used to be a space to reproduce, redesign, analyze, or express an object, but Pollock saw it as an arena in which to act, which added action and feelings of movement into his art. He was also a pioneer of the expressionist movement because his work helped define the genre. He showed artists that they could express their emotions through their artwork and thus create pieces that were more emotionally charged. Physicists were fascinated by his work because to create his famous strip paintings, Pollock would pour paint straight from a can or along a stick onto the canvas as it lay flat on the floor. And Pollock actually went to a notable length to adopt different techniques to try and alter the natural physics of how the paint would fall and hit the canvas. He avoided large droplets of paint by and he was instead able to create a natural fluidity that stretched along the canvas. And that was due to a combination of his hand speed and the distance he maintained from the canvas, as well as the viscosity of his paint, which seemed to be aimed at avoiding those notable large droplets, also referred to as coiling instability. Meanwhile, mathematicians were fascinated as they looked back on his work because his design seemed to showcase fractal characteristics, and most notably and confusing to mathematicians were the fact that fractals wouldn't be discovered for another 25 years after Pollock's most prominent pieces had already been created. So what is a fractal? I have two examples on the slides. One is the Sierpinski triangle from 1915, and one is the Koch snowflake from 1904. So a fractal is an infinitely complex shape that can present itself in numerous different ways. In other words, a fractal is a shape that's basically composed of a pattern that repeats itself infinitely many times. In the Sierpinski triangle, you could see it's very clearly the triangle in different, scaled differently to create this infinitely repeating pattern. And in the Koch snowflake, it's actually also triangles that appear on the sides, the side lengths that would create those triangles, and they just get smaller as they expand, which makes it look more like a snowflake. And fractals are actually incredibly prevalent in nature in things such as succulents, pine cones, and snowflakes. And it's also something that's referred to as a self-similar object, which means that the components of that object resemble the overall shape. So like the triangles we talked about before for each fractal on the slide. And then what are fractal dimensions? So the way that various shapes take form in different dimensions, that's something that applies to fractals as well. So a line, square, and a cube would represent shapes from the first, second, and third dimensions. So to find fractal dimensions, it's a little more complicated and needs a few terms to be defined first. There's mass, which is the word to encompass the varying measures of each shape. So the mass would be the length of the line, the area of the plane, and the volume of the cube. Scaling factor would refer to the scaling that each object takes, so you're scaling a cube down by a half. In fact, in the diagram above, the line, square, cubes, they're all scaled down by a half. Lastly, there's mass scaling factor, which is the amount of mass that has been scaled down. So in the example of the plane, even though it's been scaled in half, the mass is scaled down by a fourth because the plane would take 4 of those half scaled down squares to create the original area of the starting one. So to find fractal dimensions, let's take the case of the Koch snowflake. It's been scaled down by a third, but the mass is scaled down by a fourth because it would take 4 of those subsets of the snowflake to create the one we started with. So to find that, we would do 1/3 raised to d, where d stands for the fractal dimension, and that would equal 1/4, which is, as we said, the mass scaling factor. And that's the same as 3 raised to d equals 4. And we can solve that using a logarithm, which tells us that the fractal dimension of the Koch snowflake is about 1.262. And fractal dimensions are in the range between 1 and 2, and as the complexity and the richness of the repeating structure increases, its value moves closer to 2. So the closer the fractal dimension is to 2, the more fractally you can say it is. And then in a study entitled The Construction of Jackson Pollock's Fractal Drip Paintings, 4 academics used another technique to find fractal dimensions, and that's called the box counting method. They would convert the paintings into digitized images and then cover the image with computer-generated identical squares, which you could see on the slide. They would then analyze the statistical qualities of each fractal pattern by seeing which squares were painted or shaded gray and which were empty. And the squares that compose this grid, that mesh, get smaller. And as the squares decrease, you're able to analyze and capture the intricacies of the pattern more clearly. And so when they would calculate the fractal dimensions through this method, they would associate L with the size of each square in that mesh, and NL being the number of shaded squares. Continuing on fractal dimensions in Pollock's painting, from that same study, here are three graphs. And so figure A showed their data collection, which presented how Pollock refined his technique. The D value, again being fractal dimension, of his paintings rose from 1.12 in his early attempts in 1945 to 1.72 all the way up to like 1.89 at his peak from 1950 to 1952, which shows how his techniques were rising in fractal dimensions because their dimensions came closer to 2. Figure B takes those fractal dimensions that they found in figure A and plots them alongside the area of the canvas, which is on the x-axis. And then figure C shows the fractal dimension against the percentage of the canvas area that's covered in paint. And those plots show a correlation between the high fractal dimension values of his classic patterns and paintings and his use of large canvas and high pattern density during that time period. So there have been oppositions and studies in his hypothesis, such as one article entitled Revisiting Pollock's Drip Paintings, where 4 academics refuted the belief that his paintings contained fractals. Their theory was that drip paintings that do seem to have fractal characteristics only occur over a small range, and that could easily be attributed to chance. They also go into discussing a power law, which is when one factor is growing exponentially alongside another factor. So in terms of fractals, it's the self-similar structure. And for Pollock's paintings, there were 2 power laws and less than 2 orders of magnitude to establish each, which basically meant that Pollock's paintings are not examples of fractals. However, Benoit Mandelbrot, who is a Polish-American mathematician and is universally referred to as the father of fractals, he said, "I have extraordinary experience of these structures, and concluding that, I do believe that Pollocks are fractal." So it's a little more up to opinion, but that was just a quote that I thought was very notable. And that was everything I had on Jackson Pollock's paintings and also the fractal analysis of how they find that. Thank you.